In the last lecture, we had talked about a simple algorithm called Deutsch algorithm, in which we said that if we have 1 qubit input with 1 qubit output, the function being either constant or being a balanced function, a quantum computer can determine it in one single query, whereas a classical computer would take 2 queries. We had just begun to introduce an extension of the same algorithm by Jozza, where the difference was that the input is n qubit input and the output is still a single qubit output, namely its value could be either 0 or 1. So this is shown in this slide, that your function takes n qubit 0, 1 with that symbol multiplication n, shows that it's an n qubit input, and that is evaluated to 0 or 1. So that is the job of my oracle, and the function is either balanced or constant. The job of the algorithm is to find out which type it belongs to. I also pointed out last time that classically, in the worst case scenario, it will take n by 2 plus 1 number of queries to determine whether the function is balanced or constant, though we did point out that probabilistically it will probably take much less. But nevertheless, technically classical computation could involve of the order n step, n by 2 is same, and let's look at what the quantum computer does. The first job is to prepare a input as a linear combination of the n qubit bases. So my input is a linear combination of n qubit computational basic state. Now, since this is a rather important step in many of the algorithms, let me explain this a little bit. We have seen that a single qubit, when it is passed through a Hadamard gate, for example, if it is 0, then I get 0 plus 1 by root 2. And if it is 1, you get 0 minus 1 by root 2. Now I can combine this into a single step, saying that if my input is x, putting it through a Hadamard gate will give me 0 plus minus 1 to the power x 1 by root 2. So that when x is equal to 0, it gives me 0 plus 1 by root 2, and if x equal to 1, I get 0 minus 1 by root 2. Now, what happens if I have a n qubit state and I pass all of them through Hadamard gates? That is a sequence of Hadamard gates as is shown in the slide. So what I do is, I start with 0 in each of my register. So I will write it as 0 n. Now if n of the n zeros are passed through Hadamard gates, then what do I get? I simply get 0 plus 1 by root 2 for each one of them. Now if you expand this out, what you get? There is a 1 by root 2 there, so I will get 1 over 2 to the power n by 2. There will be terms like 0, 0, 0, 0, 0, 1, 0, 0, etc. In other words, I will get a linear combination of each of the n qubit basis states, and each one of them appearing with the same strength. So this I will write as sum over x, where x is n qubit basis state. So this is simply a shorthand notation for 0, 0, 0, 0, etc. For example, supposing, just to give you an idea of what happens when I start with 2 zeros. So what happens to this? When it is passed through Hadamard gate, I get 1 over n is equal to 2. So I get 1 over 2, and this would then be 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, and a very similar statement I can make for any number of states. So this is what we will frequently refer to as the uniform linear combination of n qubit basis states. The target in which my output will come is, it is set to 1, and I pass that through Hadamard gate. As you know that this is 0 minus 1 by root 2. Now here in this picture, I am indicating the state of the system by psi 0, psi 1. So what I do, this is a very common nomenclature, that since we have said that this is the direction of logic flow, essentially it's a time diagram. So my initial starting point, which is 0, 0, 0, 0, and last one being 1, is psi 0. When all of them are put through the Hadamard gate, my state is psi 1. Then this thing is passed through an oracle, and so the out after the oracle, what comes out, this will be the same for the inputs, but there would be a difference in the output, and then psi 2, and then after the first qubits are put through the Hadamard gate, I will call it as the psi 4 or psi 3, doesn't matter. Now let us look at what am I getting. So we have said already, my input is uniform linear combination 1 over 2 to the power n by 2, sum over x equal to 0 to 2 to the power n minus 1. There are total 2 to the power n number of states, x. The target is 1 passed through a Hadamard gate, which gives me 0 minus 1 by root 2. So what is my output? Now this output is an entangled output. It gets entangled because the function that it calculates is fx corresponding to every x that is here, but when that gets XORed with 0, I get fx, but when you XOR it with 1, I get a bar of x. So as a result, I will be writing my output as 2 to the power n plus 1 by 2, this is product of this with this, summation over x equal to 0 to 2 to the power n minus 1, x because that part is not changed. Now what happens here is I get fx because the oracle calculates f of x, XORs it with 0, and I get an fx. 1 when it XORs it, I get a bar of x. So this is what I got. Now we have already stated that I have two types of function. Fx is equal to either 0 or 1. Since fx is equal to 0 or 1, this quantity is either 0 minus 1 or 1 minus 0, depending upon what the value of fx is. So you can write this then as everything else remains the same. Minus 1 to the power fx, 0 minus 1. So this is that phase factor that comes up because of the fact that I could either get 0 minus 1 or 1 minus 0. Let us write it in a slightly different way, because you notice that I can associate this phase factor with the first n qubit itself, because there is a minus 1 to the power of x. This is independent of x. So therefore, my output can be written as 1 over 2 to the power n by 2, or 1 over square root of 2 to the power n, sum over x, limits I have written once, minus 1 to the power x fx x, and the second, the target qubit, is simply 0 minus 1 by root. Now let us look at this, that supposing now this first n qubits are passed through a Hadamard gate, to show that all of them are passed through a Hadamard gate, that is the notation I use. Now what will happen? Now firstly I know, this is a little bit of an algebra. So firstly I know that when I have xi, I pointed it out earlier, xi passed through a Hadamard gate gives me 0 plus minus 1 to the power xi 1 by root. Now there is a quicker way of writing this, and that is equal to 1 by root 2 sum over k equal to 0 to 1 minus 1 to the power xi times k, or if you want it to be a little more symmetric, let us call it ki, xi ki, then ki. Now you can see that this is the same, because if ki is equal to 0, I get minus 1 to the power 0 and 0. If ki is equal to 1, I get minus 1 to the power xi, this way. So if I then expand my x as equal to x n minus 1, x n minus 2, etc. up to x0, then when the input, the first n qubit inputs are passed through the Hadamard gate, what I get can be written as 1 over 2 to the power n by 2. So each one of these terms that was there, I will write it in this form. So therefore, I will have sum over k n minus 1 equal to 0 to 1, and like that up to k0 equal to 0 to 1. I get minus 1 to the power xi ki, and of course kn minus 1 up to k0. So one phase factor from each of the terms. Now I can compactly write this. So 1 over 2 to the power n by 2, I will take care of the remaining factors later. Sum over k, so k is simply the state, so k is my state, kn minus 1 up to k0, and this one I will write as minus 1 to the power x dot k. Now what is x dot k? X dot k is basically x0 k0 plus x1 k1 up to x n minus 1 k n minus 1. So this is, if you like, bitwise product sum. So let me write it. sum of bitwise product x dot k, something like a scalar product the way we write it k. So now going back to my original input, before I had put it into Hadamard gate, there was another 1 over square root of 2n factor there and a minus 1 to the power fx there, and of course there was a summation over x. So when I combine all this, I get my output to be given by 1 over 2 to the power n sum over x equal to 0 to 2 to the power n minus 1, k equal to 0 to 2 to the power n minus 1, minus 1 to the power fx which was already there, plus x dot k which we just now calculated, state k, and of course 0 minus 1 by root 2. So this is my general expression. Now what I will do now is to evaluate this expression for the case for which fx is constant and also for the case for which it is balanced, and we will see what comes out of it. Now let us suppose fx is constant. Now if fx is constant, then look at this one. So I get a constant phase factor will come out of it, and I will ref with minus 1 to the power x dot k. So the phase factor will have equal number of positive and negative terms because of minus 1 to the power x dot k, and this will cancel out, excepting for the case for which my k happens to be equal to 0. So therefore, for the case for which k is equal to 0, if fx is constant, I get minus 1 to the power 0, all of them are adding up, okay, and so therefore my first register will have the state 0. So fx equal to constant, the first register will be in state 0, of course n qubit state. Now let us look at the same structure again for the case when the function is balanced, but this time I cannot actually have that simplification because there are too many terms there, but I do something else. Let me find out what is the coefficient that comes out with k equal to 0. If you refer to the slide again, you notice that if I take k is equal to 0, then this k dot x of course goes away, and I am left with only minus 1 to the power fx, and there is a sum over x equal to 0 over minus 1 to the power fx. Now obviously, since the function is balanced, there are as many fx equal to 1 term as there are fx equal to 0 terms. So therefore, this sum over x, notice that there is no x elsewhere, the k dot x term has gone away. So that would be equal to 0. So notice immediately that there is a big difference between the two cases. In the first case, when the function is constant, my first register will contain only the state 0. But if the first register measures anything else, then the function must be balanced. So once again, a single query determines whether my function was balanced or not, and that is obviously a great improvement over the corresponding classical algorithm. This has a very trivial extension to a problem which is known as Bernstein-Vazirani problem. Now, in the Bernstein-Vazirani problem, we have an input string x equal to xn minus 1 x0, and there is an unknown string a. This unknown string's information is known to your oracle, and what we do is that the oracle calculates for a given x fx equal to a dot x, where a dot x is the sum of the bitwise product that I mentioned just now. That is, a dot x is equal to this, and this is a single qubit output. So therefore, this is essentially a Deutsch-Jozsa problem, with the change that your fx is a function which is equal to a dot x. The problem in Bernstein-Vazirani problem is to find out what is this unknown string a. Now, what about classical searches? The classical search requires n number of queries, because I can evaluate what is, for instance, f100, f010, and find out immediately what are these things. Should be an minus 1, an up to a0. So therefore, it requires n number of queries. Now, basically what I have drawn here is the same picture as that of the Deutsch-Jozsa, with the oracle being that oracle which computes for a given x, a dot x. So let us look at that. What I have done in the second line of the slide is to rewrite the Deutsch-Jozsa expression for the output, accepting that in place of the fx, I have written a dot x. So this is a dot x plus k dot x. Now, what we can do is to remember that the sum over x is only related to this phase term. So we say that we are going to find out what this sum over x is. Now, we know already that this is an n qubit state, and this is simply minus 1 to the power this. So therefore, this sum can be written as product over I equal to 1 to n, and xi which can take the value 0 or 1. So it's a minus 1 to the power xi ai plus ki, because that was my definition of the bitwise sum. So if you perform this sum over xi equal to 0 to 1, there is just two terms here. When xi equal to 0, it is 1. When xi equal to 1, it is minus 1 to the power ai plus ki. So that this sum over x contains this factor. Let me just repeat this here. I equal to 1 to n, 1 plus minus 1 to the power ai plus ki. So this is what sum over x gave. The other things of course remain the same. Now let us examine what this term is like. Now notice there is a product of I equal to 1 to n. So excepting when ai equal to ki for each I, there would be one term at least for which this term which is being in the product, one of the terms at least will be equal to 0. So therefore, the ai equal to ki, that is what will come out of it in the sum. So if I measure the first register, then I determine what is this string ai with certainty. So once again, we have determined a classically, I won't say a difficult problem, they are all reasonably simple problem in classical computing also, but what we have done is to find in a single query something which took many queries in classical computing. These three simple algorithms were illustrated to tell you about the inherent or intrinsic power of quantum computation. We will be later doing two major algorithms where the quantum computer has a great advantage over classical computation.